Okay, we're about to do an AC problem. I find that, and really most of my students find that AC problems, when we're working them out, are actually much easier than DC problems. They're really more straightforward. There's not a lot of stuff to memorize, and so you can just kind of start at the top and work your way to the bottom. And what I mean by that is using this formula sheet. So what we're going to do to answer this problem that I have, and I haven't showed you yet, is we're literally going to start at equation 1, and we're going to work our way all the way down to equation 13, and somewhere in between we will find the answer to the problem that we're being asked. And so the key thing in AC problems is remembering which side to use. This over here is for series AC circuits, and so these are only to be used for series AC circuits. These are for parallel AC circuits. These are only to be used for parallel AC circuits. If you find yourself working a parallel AC circuit and you can't find something and you jump over here to use an equation, you are wrong. You will get the problem wrong. You cannot do that. It will not work out for you. So, looking at this problem, by now you should be able to identify that this is a series circuit. We have one path for current to flow, and so by definition that makes it a series circuit. Here we have 110 volts AC, so alternating current coming out of our source. So kind of like our battery, but we don't represent batteries in AC because batteries are DC, so we just say, hey, this is some kind of signal generator. It's generating an AC wave, and it's coming out as 110 volts AC. The frequency of the output is 60 hertz. We have a 8 ohm resistor, a 100 microfarad capacitor, and a 0.021 Henry inductor. One of the other things that's kind of difficult for students to get their mind wrapped around is the additional units that we're having to deal with. So farads for capacitors, Henrys for inductors. We got this hertz thing going on. If you can memorize that, you can really work through these pretty easily. These just take some studying and some memorization there. So again, this question says find IT, and that's going to be the current flowing through the entire circuit. Find E sub R, and that's going to be the voltage drop across the resistor. E sub L, that's the voltage drop across the inductor, and E sub C, which is the voltage drop across the capacitor. And lastly, it wants us to find the phase angle or the phase shift between voltage and current. And so we can do all of that simply by starting at the top here and working our way to the bottom. So again, with every other problem, we're just going to write down the formula. So number 1 is X sub L equals 2 pi times the frequency, and that's what this script F means, times the inductance. And so over here we're just going to rewrite 2 times pi times the frequency of 60 hertz times L, and remember L is the variable, but H is our units, and so we're going to have 0.021. And X sub L, if you remember from the lecture, they always come out as ohms. Okay, so we'll punch that in the calculator, and we'll come out with 7.92 ohms. And good there. Let's move on to number 2. Number 2 is X sub C is equal to the reciprocal of 2 pi times the frequency times the capacitance. And then we'll plug in some values here. So we have 2 times pi times a frequency of 60 hertz times a capacitance of 100 microfarads. So that's 100 times 10 to the negative 6. And it's important that we don't forget to put it in the calculator that way. That will really mess you up if you forget that. So X sub C, if we correctly put that into the calculator, we're going to come out with 26.5 ohms. All right, moving on to number 3. Number 3 says that X sub T is the absolute value of X sub L minus X sub C. So X sub T is X sub L minus X sub C in the absolute value. So plugging in our values here, X sub L was 7.92 minus X sub C, which was 26.5, and then we're going to take the absolute value of that, and that's also going to come out to be ohms. This brings us to an X sub T value of 18.6 ohms. So 18.6 ohms. All right. Number 4 is our equation for impedance. Now we can do this a couple of different ways here. We can either do it in terms of X sub T and or we can do it in terms of X sub L minus X sub C. So let's just, since we have X sub T, let's do it in terms of X sub T. So Z equals R squared plus X sub T squared, and then we're going to take the square root of all of that. And so Z, our resistance here is 8 ohms. Pull that down a little bit, 8 ohms, so it's going to be 8 squared plus X sub T squared, which is 18.6 squared, and then we're going to take the square root of that. And if we punch that into the calculator correctly, we end up with 20.2 ohms. Okay, so what does this Z represent? This Z represents the combined resistive effects of the resistance, the capacitive reactance, and the inductive reactance, right? It has them all baked in there. So we still haven't found any of the answers we're looking for, but we will. They're not asking for a power factor, but power factor is pretty straightforward. It's just R divided by Z to get a power factor. We do need the power factor to get our phase angle, so we'll work our power factor. Power factor is R divided by Z, where R is 8 and Z is 20.2, and both of those are ohms, and so the ohms will cancel, and power factor comes out to be unitless because our ohms cancel. And so the power factor comes out to be 0.4, and that's it, no units. Throwing that into our phase angle is going to be the inverse cosine of our power factor. And so we say the inverse cosine of 0.4, and that comes out to be 66.4 degrees. All right, and that's our phase shift. Now, at this point, if we remember Eli the Iceman, we see that our capacitive reactance is 26.5 and our inductive reactance is 7.92. So we are actually more capacitive than we are inductive, and so that's going to put us in the Iceman category. And since we're in the Iceman category, we know that E lags behind I, or I leads E by 66.4 degrees. That's what that means. That's our phase shift. So number 7 is going to bring us to, well, this was the first item we were looking for, so we can kind of check that off here. Boom, got that. I sub T is number 7, so I sub T equals E sub T. And the formula sheet says Z sub T. There's Z and Z sub T are one and the same, okay? When you find Z, remember Z is the total resistive, the effects of the total resistive forces, so it is a total in and of itself. So Z sub T equals Z. The E here is 110 volts, and that's going to be divided by our Z, which is 20.2 ohms, and that's going to give us an I sub T of 5.45 amps. And that's our second one that we found. Number 8 is the apparent power. And so if we just took this E times I at face value, right, not factoring in any type of phase shift, that's what apparent power is. And so apparent power is going to be equal to E sub t times I sub t. And so the apparent power is E sub t, which is our 110 volts again, times our I sub t, which is 5.45 amps. All right, once you put that into the calculator, you end up with, actually we don't need that because that doesn't feed into any of the other things we're asked about. So I'll go ahead and do it real quick just to have an answer, so don't leave you hanging. 110 times 5.45 amps is going to give us an apparent power of 599.5 watts. So power in AC is still measured in watts, nothing's changed there. If we wanted to, we could go on and find our true power based off our power factor. We're not being asked for it here, so I won't belabor that point. Moving on to number 10, so that we can find this E sub R. E sub R is going to be I sub t times R. And so E sub R is I sub t times R. So I sub t is this value here is 5.45 amps times our resistance of 8 ohms, which gives us a voltage drop across the resistor of 43.6 volts. So there's another answer. Check that one off. Number 11 is our E sub L, and that's going to be the voltage drop across the inductor. Notice now we're dealing with the resistive force due to the inductor, so it kind of looks very similar to Ohm's law, except we're replacing R with the X sub L. And so it's I sub t times X sub L. And so I sub t is that same 4.545 amps times the X sub L of 7.92. Which gives us a voltage value of 43.2 volts. So there's our next to last one we were asked. And then number 12 is going to be E sub c equals I sub t times X sub c. And this is the voltage drop across the capacitor. So 4.45 amps, same as it was before, and then X sub c is this 26.5. And that's going to give us a voltage of 144.4 volts. Now you may be asking, well, how in the world is that 144 volts and we only started out with 110 volts AC? Well, remember, this is RMS value, right? So this is actually 70.7% of the peak value, and so there's actually more voltage, AC voltage here, than what this leads us to believe. There's a peak voltage much higher than this, and so that's how we're able to get this 144.4 volts. And then if we wanted to check ourselves, we can actually execute equation 13 here, and we should be getting an E sub t value that is very close to that 110 volts up there. So E sub t is E sub r squared plus the difference in E sub L and E sub c squared, and then we take the square root of this. And so E sub t is E sub r, which is 43.6 squared, plus E sub L, which is 43.2, minus 144.4, because that's E sub c, and then we square that, and that gives us, let's see what that comes out to be. So 43.2, I'm doing the inside the parentheses first, so 43.2 minus 144.4 equals, square that is going to be, we'll say plus 10,241.44. Now, if we do 43.2 1,900.6 squared. That's going to be 1,900.96, and then we take the square root of that sum. So let's add back in the 10,241.44. That's going to be everything up under the radical here, up under the square root, and then we take the square root of that, and lo and behold, we get an e sub t that is extremely close to our starting e sub t. And you may be asking, well, how come it's not exactly? Well, we did a lot of rounding throughout all of this problem here, dropping off numbers, doing a little rounding, so that's why our number's not exactly what we had started out with up here. And so if we get something that close, we're perfectly fine. That means all of our numbers up above should be correct. All right? And so just to kind of backtrack, all we did was start and identified our type of circuit. So it's an AC circuit and it's a series circuit. And so we're just going to use the series side of the formula sheet. And we just worked top to bottom, number 1 all the way through number 13, and we found the answers we were looking for. If we had a parallel circuit, we would do the exact same thing, except we would use the equations on the right hand side, and we would never ever go jump across and grab an equation from the parallel side. If you can't find something that you're looking for on the parallel side, it means you just haven't looked hard enough. I guarantee you that the answer to the question that they're asking you for a parallel circuit will be provided within one of these equations right here. All right? A lot of students, just to kind of highlight some pitfalls, a lot of students, what they like to do is they won't write everything out like I did here. They'll just start hand jamming things into their calculator. They'll start reading these numbers and start hand jamming without writing it out. The pitfall of that is if you accidentally keystroke the wrong key, you won't notice it until it's too late, and you'll trust your calculator too much and you'll write down a bad answer. If you write everything out, this will kind of keep track. You can actually go, okay, one hand's here and one hand's on my calculator. So I'm going to say 2 times pi times 60 times 100 negative 6 equals, and that's everything under the bottom, and I still got to take the reciprocal, so hit the reciprocal, and that comes out to be there. If I keep a finger over here, keeping track of what I'm supposed to be putting in and using my other finger to punch the keys in, I'm more likely to not make a mistake. Okay, so if we start doing this, it gets a little crazy and we start missing numbers, but if I'll keep my finger over here and my finger over here, I'm very less likely to make a mistake when putting things in the calculator. All right?